the things that we were doing yesterday. And intended to prove Baire's theorem. Different versions of Baire's theorem. And then we're going to do some of the consequences essentially of the Baire theorem. We talked yesterday about those consequences. In particular, we will kind of but use Baire's theorem to prove uniform boundedness principle, open map theorem, and closed graph theorems. Big three theorems of function analysis. Baire's theorem is not really a result in function analysis, but it has consequences in function analysis. So what was the statement? Let's recall. We said that let omega d be a complete metric space and let imagine that you have a countable sequence of closed sets. Sequence of closed sets used subsets of omega. These are not just random subsets of closed sets, but they are closed sets such that when you take the union of all these closed sets, they're going to cover everything in omega. Okay? So if you have a complete metric space in such a sequence of exhausting sequence of closed subsets of omega, then there exists a natural number, in other words, an index and
x
a point in omega
and the radius,
and
some radius positive,
such that if you have a ball of
entirely sitting in
centered at x with the radius r is entirely sitting in this particular closed set with the index what? Okay. In other words, what does this proposition is telling us? That if I have a complete metric space with some exhausting sequence of closed subsets, then at least one of these closed subsets is going to contain one open ball.
सर एक रिमार्क ये भी है ना, in particular Banach, Hilbert सब के अंदर ये true हो जाएगा.
Yeah, obviously. See, nothing too much interesting, but we're going to see some of very interesting consequences of this result. Okay? So you have the countable, number of closed sets which exhaust omega, and the Baire's theorem tells us that among these countable number of closed sets, at least one of the closed set, which we call, for example, say M, is going to contain a ball, is going to contain an open ball. Okay. Alright. How are we going to prove? Before writing a proof of this theorem, let me maybe do a lemma here. Okay. And we did this lemma yesterday, so I'm not going to repeat its proof. Okay, I'm just going to state it, and the lemma is, something called the principle of
nested balls.
Principle of nested balls. Okay. We did something similar also in real analysis for closed intervals actually, but now it's a kind of a generalization of that result. So it is something of dependent importance in itself. So what does the lemma is saying? The statement is this, that if you have a complete metric space, and you have a decreasing sequence of closed balls, you have a decreasing sequence of closed balls, okay, such that two things hold. Number one, that the sequence of radiuses go to 0. In other words, somehow these balls are shrinking, okay, and the sequence of the centers of these balls converges to a particular point, which is x, as n goes to infinity. As n goes to infinity, then if you take the intersection of all these closed balls, okay, so that will be xn Rn, you're going to get a singleton which is pretty much xn. You can't see that? So rewrite it here. Can you see this part? Not even this part. Then, if you take the intersection of these closed balls, okay, Rn, that intersection is going to be the singleton. What would be that element inside that intersection? Is going to be the limit of the sequences of the centers of the ball, basically, to which.
So this limit was also in conclusion, not in the assumption. Xn goes to x. Was also in the conclusion.
Which one?
Xn goes to x.
So it's a conclusion.
We are putting it here in the assumption because
okay.
we proved.
Okay. So then, right? So in other words, if somehow, and it makes sense, just think about it. It makes sense. So in other words, you have a number of balls. Okay, so you have a ball within a ball, and somehow within a ball, and so on and so forth. Okay. So it's like if these balls, which might have a different, what do you call, radiuses. You know, if you keep on decreasing the radiuses, you know, these centers are somehow going to basically stabilize that. They are going to get to something, you know, something specific. Okay. So intuitively this makes sense. So this was the result that we did yesterday. As I said, that we did similar kind of result for closed interval, if you remember. Okay. That if I have, you know, closed interval and within closed intervals and so on and so forth,
their intersection is going
to be similar. So that's a slight generalization of what you did. Another thing that I would like to mention, there are different versions of the Baire's theorem. Okay. Available in the literature. Okay. So that's one version of it actually. Okay. But when you will see, for example, the actual version of the Baire's theorem, it actually says that if you have some a countable collection of open sets which are dense in a metric space, then their intersection is also going to be dense in the metric space actually. Okay. It's like if you have loads of open sets in a metric space, complete metric space which are dense, then their intersection will also be dense. So that's what you call the actual version of Baire's theorem. And in exercises, there is a connection of this result with, with the actual version as well. That how you can deduce the actual version of Baire's theorem from this actually. Okay. Why we are using it? We are using this version of Baire's theorem because in order to prove the results that we are interested in, this is sufficient actually. Okay. So that's why we are kind of more interested in this version of Baire's theorem. Alright, so let's move ahead and let's get into the proof of this result actually. Okay. So we have all this information with us, and what we are interested in showing that at least one of the ball is going to contain, one of the closed set is going to contain an open net. Okay? We're going to do it through the contradiction. In other words, we say that suppose not. Okay? Suppose not. In other words, imagine that you have all these closed sets which exhausts omega, but none of
subsets
closed sets contains any open ball. Are you getting the point? And then we're going to show. So what I'm going to show basically that there is an element in omega which is not in any of these ANs actually. So what this is going to show is that these sequences of closed sets are not exhausting omega. Okay? So in other words, this equality is not true. So I'm going to, by assuming contrary, I'm going to get a contradiction. This factor. So that's what I'm interested in. Okay? So our objective is to find an x which is in omega but not in the union. Alright? Now, consider this set actually. So it's like an A1 complement, in other words, omega minus A1. Okay. What we can say about this set? Why this set is an interesting set? Okay, doesn't contain any point of
एक तो open हो गई.
Can this set be an empty set? A1 complement be an empty set? Okay, just think about it. If A1 is whole of sigma, okay, then this result is trivially true because omega contains
every ball.
Ball actually. Okay. So if we assume that A1 is whole of omega, so in other words, A1, so if we say that A1 is whole of omega, then containment of such a ball is trivial actually. Okay, it's going to contradict again our assumptions. Okay, so obviously A1 cannot be omega.
And hence it is not non-empty.
So if A1 is not omega, then
this is not.
It shows that there are some elements in A1.
It's non-empty.
Are you getting the point? Okay. So consider A1, which is omega minus A1. Indeed, A1 cannot be whole of omega. Okay. Hence, so there exists an x1 in the set A1 complement. Okay. There exists a set x1 in the A1 complement. Now, so if I make a picture roughly, so if this is my A1, okay, if this is my A1, and this is my whole omega, then x1 is somewhere here. Okay? Then x1 is somewhere here. And then I can easily see that, okay, obviously this point is going to have some distance from this whole set. And if I take the half of the distance, for example, from this whole set to x1 and draw a ball on it, then this ball is going to be different from the A1.
Of course.
Okay?
Open ball.
Open ball or even closed ball.
Okay.
Are you getting the point? So there exists x which is A1, and I would say that since A1 is closed, so there exists a small enough radius. Okay, so since A1 is closed, so A1 complement is open, and x1 is a point on
in A1 complement.
In A1 complement. So since A1 complement is open, so you can draw a ball on x1 which is entirely going to sit inside A1 complement, and hence that ball is going to have nothing with
A1.
Okay. So there exists a radius, okay, small enough. We can give it a name. Small enough such that A1 and the closed ball with the radius x1 and with the center x1 and the radius r1 has an empty intersection. Okay? Is it making sense? Alright? Now, since A2 is closed, you have to, so this is going to be kind of a recursive argument. Okay? So you have to be careful. Now the next is that, let's see that A2 is closed. Okay? Since A2 is closed. So if A2 is closed, so you see, one of the things that you have to be careful that I'll play between the closed ball and open ball. Okay? So you have to be careful that where I am talking about the closed balls and where I am talking about the
open balls.
So since A2 is closed, okay?
By same our previous argument.
Okay. Can I say now? Can I say I have A2? What would be the relationship between? Let's reflect upon it. What would be the relationship between A2 and the ball of the radius x1 r1? The open ball, not the closed ball. What would be the relationship between these two? Because you have assumed that none of these ANs contains open ball. So obviously A2 is not going to contain it.
Open ball.
Okay, so it's not going to contain
closed ball. Open.
Then it's valid.
Sahi.
Closeness we're going to use when we're talking about intersection, but openness when we're going to talk about such a relationship. Now, what is the meaning of this not being subset of A2?
In the complement of A2.
Well, it's not necessary that if something is not a subset of some set, it must be. Huh? Intersection example. What is the negation of being subset?
Sir, अगर A B का सबसेट नहीं है तो complement का
why one set is not a subset of other?
There exists an element.
So we're going to say that this implies that there exists
x2
an element x2
in the ball
in the ball be x1 r1
such that it is not in the A2.
x2 is not. So you don't need to think too much, you just have to think a bit cleverly. Is it making sense? Now I'm going to do what? I'm going to do the same with the x2 what I did with the.
एक और ball.
So I have a ball and I'm going to have a ball within a ball actually. Okay, it is going to be away from. So let's see the next one. And you know, somehow I'm interested in using the principle of nested balls. And don't forget our key, intention that we would like to do, that we would like to find an x in omega which is not in this union.
Okay.
Any of these A and C. Hence, is going to contradict our without this connection. Okay? So there exists x2 such that there exists x2. And then again, since A2 is closed, okay, and Bx1 R1 is open.
So ये इसमें नहीं आएगा.
Okay, so there exists a small enough R2 such that what happens? Such that A2 is not intersecting with the closed ball x2 R2, and the ball with the radius x2 R2 is entirely sitting in x1 R1. Okay? Or even I can make this even more weaker, that it's even sitting in this actually open. And since this is sitting in open ball, it can also sit in.
Sir, A2 से intersection इसकी phi क्यों होगी, ये इस पे मसला हो रहा है. A2 intersection ball, closed ball, ये phi क्यों हो रहा है?
Why? Because just think about it. This guy is a part of this actually. And this has what?
This is not entirely an A2 complement. It has, maybe it has to do something with it, with A2.
Okay. So let's try to figure out why this would be the case. Okay.
In one scientific.
So A2 intersection. Since A2 is closed. Okay. So yeah. We're gonna run the same argument. We're gonna say that since A2 is closed and this is open, so this is not a part of A2. Okay? By the given assumption. Okay. Hence, the A2 intersection. So there exists some radius R2 which is positive, such that this intersection is empty, and the ball is clear.
Sir, can I say na कि ये open ball is an A2 complement?
Yes. Is it making sense? Now, if this is the case again, what we're going to do? What would be the next step? Can A3 again, since A3 is closed but does not condense, this second x2 R2 ball, can A3 contain it? So it can't actually.
By our assumption.
By our assumption, so by our hypothesis. So what does it mean? This means that there exists an x3 okay, in B x2 r2, okay, in B x2 r2 such that this x3 is not in A3. Okay, and what we're gonna do? We're gonna play the same game actually now. So let's draw, a ball on this x3 with such a small radius that it doesn't intersect with the A4. Okay, maybe A3, and you have another element in this basically. Okay, and similarly, let's make it prosaic. Since A3 is closed, so it's like a story. It's not that difficult. You have to just be careful. So since A3 is closed and B x2 r2 is open, so there exists a radius r3 which is positive. Okay, there exists a radius r3 which is positive, such that that A3 intersection
with this ball closed,
x2 x3 r3 is empty, and B x3 r3 is contended. The ball with the radius x2 r2. I can put the closed interval as well. What do you call the closed ball as well? It's not going to make any difference, and hence this is contained and so on and so forth. Okay. So in this manner, what I'm gonna do?
Continue. A ends up to n, pass some n.
In this manner, I can continue. In this manner, we can find a sequence
of balls,
of nested balls. B xn Rn, Rn, where n is a set of natural numbers, such that, what is the key thing? That the intersection of these balls
is singleton.
Okay, with the sets An is empty. Okay,
for all n
is empty. Obviously, for all n in n.
Very natural.
Now here's the thing. What we are doing actually, just think about it. At each step, what should be the relationship between the radius 1 and the radius 2? What do you think?
Radius 2 is smaller than radius 2.
So radius 2 is smaller than radius 3, and radius 3 is smaller than radius 2. Okay? So what we can do is, in other words, what we can do that we can choose this sequence of radiuses in such a clever way, okay, that in long run that sequence of what do you call it?
Converging to 0.
So converges to 0.
It is decreasing and lower bound 0.
Yes. So what we can do is that so as this sequence Rn, okay, of radiuses is decreasing, so we can arrange it. We can arrange it By arranging, we can choose these Rn's in such a way that Rn goes to 0. Okay? As n goes to infinity. As n goes to infinity. Now what does this mean actually? This means that you have a sequence of nested balls in which the radius is going to 0. Then we are